So it's a great pleasure to be welcoming you all to the Green Family Lecture Series. My name is Dima Shlichtenko. I'm the director of IPAM. So I want to start by saying thanks to a number of people. First of all, the Green Family Lecture Series has been established at IPAM through a very generous donation by Mark Green Family, and Mark and Catherine are here. So I would want to give a big round of applause to them for endowing this lecture series. So as many of you know, IPAM is a math institute funded by the National Science Foundation, and our mantra is to, summarized in our slogan, math changes everything. So what we do is we run long and short programs in mathematics and related disciplines, and what IPAM does best is connect mathematics and mathematics or other disciplines together so that we form research communities that then go and change the world. That's very simple to say, but it actually happens. That's what's magic about IPAM. The purpose of the Green Family Lecture Series is to bring eminent scholars to IPAM, and you can go to our webpage and consult the list of past speakers. They've been extremely accomplished people. There have been a number of people that have received the highest accolades in their science. In mathematics, as you know, one of the highest accolades is the Fields Medal, and our speaker tonight, Vaughan Jones, is no stranger to big accolades. In particular, he received his Fields Medal in 1990 for what is now known to be as the Jones polynomial. And as many of you know, his work has set off an absolute revolution both in low-dimensional topology, but also in areas such as quantum field theory, von Neumann algebra, subfactor theory, and so on. So it's really a great pleasure to have him with us. Vaughan has had a long history of connections with UCLA. In fact, he was here in the early 80s as one of our Hedrick assistant professors. And he was telling us that actually some of the early work that he's done related to what became the Jones polynomial is actually related to UCLA. So there's a long connection here. And certainly has visited this campus many times, and he's had many collaborations on campus. Vaughan has received many honors besides the Fields Medals. He's a member of the National Academy of Sciences. He is actually Sir Vaughan Jones, and next to his name there's a long list of undecipherable symbols associated with this, which I will not try to repeat for fear of getting them wrong. He also has been elected to be a Fellow of the American Mathematical Society. He's a Fellow of the Royal Society and has won many, many other prizes. So without further ado, let me just introduce Vaughan Jones, who will speak about what is it about the plane. So thank you so much. Before I go, I forgot to say, there will be a reception at IPAM, not here, but at the IPAM building immediately following Vaughan's talk. And I also would like to thank the IPAM staff for putting on tonight's show. So thank you again.
Well, thanks, Dima, for the introduction, and thank you all for showing up. This kind of talk is actually one of the most difficult things around to prepare, because you are told in no uncertain terms by the organizers and everyone else that it is a public talk, that the people who you're going to be talking to are the general public, and you're not supposed to suppose anything about, even calculus. And you show up, and there are all of your colleagues. So this means that you have to sort of dive into it and somehow improvise a little bit according to the expressions on the majority of faces in the audience. But anyway, I've done it before, so hopefully those of you who are general public will enjoy the talk, and those of you who are, know all this stuff already will also enjoy the talk, but perhaps for other reasons. So let me start off by, as Dima said, I have rather impeccable UCLA credentials. I'm just about as UCLA a person as possible to get without working here. I did work here once upon a time, but it's also true that both of my kids, two of my three kids were here. You'll see this one here. This is the Bruins dad sweatshirt, which I qualified to have by having my son he spent his freshman year, he was a music student, and there was a cello teacher, he plays the cello, that he particularly wanted to study with, but for some reason that got a bit cross-threaded and he left after a year, which was too bad. He was having a great, if smelly, time in one of the dormitories. But then later on, my eldest daughter, Bethany, did law here. And she went all the way, she graduated, that's her right there. And you'll recognize the UCLA buildings behind us. So that was a graduation ceremony. And I was looking to get this photo to show you. I looked through some of the old files and I found some interesting ones, because after the graduation ceremony we had a party, and I was clever enough to take someone was clever enough to take some photos. So I'll show you a couple of those. Here's some people that you will recognize. Here's the gentleman who was supposed to introduce me but forgot his notes. There's his wife Corina, there's Olga, and one of the boys, I'm not sure which one, Dima. Okay, now, so I'll just show you two of these, but the second one is interesting. There's some people in it that you might recognize. This is Feng Shu, and this is Tiffany, his wife. This is my future son-in-law, my current son-in-law. But the interesting one, I think, is this guy here. Anyone? This for Tinseltown, you might know. This is Colin Trevorrow, who was the director of Jurassic World. And this is his wife. And he was actually a friend. He was a good friend of Bethany's. He was a neighbor of ours when Bethany and he were in the same school when they grew up. And in fact, his wife, Isabel, was introduced to him through us, actually. So that's, yeah. Anyway, I'm not here to tell you all these social stories. I'm here to talk about the plane, and it's how the plane is just somehow much deeper than it seems. So, I mean, for instance, you can even see it right here, right? This is a picture in the plane, right? Everything about this picture is actually happening in the plane, and yet it gives us a perfect representation, or essentially perfect representation of a three-dimensional situation. Maybe if you tell that to a dog, he might not agree, but certainly to the human, there's enough information there so that we feel it's so three-dimensional, we feel like we could actually stick our hand in there and go along the table and shake hands to a person down there. So one of the themes about this talk is that somehow the plane, this two-dimensional space, is completely adequate for representing three and more dimensions, which is quite stunning. It's not true of the line, but of the plane, you really, when you jump from 1 to 2 dimensions, you get a huge gain in the things that you can see and represent and discuss. Okay, now in the other direction, our senses seem to have also projected, since we have this sort of planar vision, we have projected our planar vision on all kinds of things, and in some cases we actually get it wrong because of this planar thing. So here's the example that I want to give. It's been my great pleasure over the last now 13 years to have a beach house, you might call it, at Bodega Bay in California. It's about 60 miles north of San Francisco. It's where Hitchcock made the movie The Bird, so there are indeed a lot of birds around there. But on just about any cloudless night, which they do happen up there, then I will sit out on the deck and watch the sunset, and sometimes there's a moon, and the half moon would be a typical one. And here's the phenomenon which has puzzled a lot of people that I've told it to. As you see the sunset, right, the sun's setting over there, we're right over at Jesse, it's going down there, and the moon is up here. Right, now the light is coming from there on a straight line, we all agree, hits the moon, and then sort of by symmetry, if it's a perfect half moon like that, if you take the perpendicular bisector at this point here, take a straight line out there, that must point to the sun, right? The sun, you can't argue that the light was a bit slow getting from the sun to here. That doesn't work because it's, okay. So you look up and the answer is it doesn't. If you draw this straight line and the sun is just at the horizon or just below, then that straight line points well above the sun. So what's going on? Well, I'm sort of ashamed to say that I spent many an hour thinking of all kinds of spurious reasons why this was true about the shape of the moon, and maybe the moon wasn't round. Anyway, I'll leave you to think about it. But the reason is simply that you are projecting your two-dimensional vision of things, and the straight line in 3 dimensions isn't really a straight line when you perceive it. Okay, so think hard about that. As I said, a lot of my friends have, almost got into a big fight about it, and I just ended up by saying, let me know when you agree with me. So there we go. So that's the plane, right? The plane is very embedded in our consciousness, and we can understand higher dimensional things just by looking at pictures in the plane. Right, so mathematicians are not the only ones who have been fascinated by the plane as opposed to 3 dimensions. There's a famous book called Flatland, written by Edwin Abbott, Flatland, A Romance of Many Dimensions. There's a picture of Abbott himself. He wasn't a mathematician, although he did study mathematics, but he was a high school teacher in London in the late 19th century, in the Victorian era. And he wrote this book about people who lived in a two-dimensional world and some of the advantages and disadvantages of living in that world. I haven't reread it recently, but I have to confess that my most enduring memory of the book is about the difference between the sexes, that men in Flatland are sort of triangles or squares or regular hexagons or something like that, whereas women are unfortunately reduced to one-dimensional creatures. So they sort of wander around and they're in the house and so on, there's a man and a woman, and being one-dimensional, they're very sharp. So if they encounter the man the wrong way, they will slice him right in half. So the women are forced to go around the house, singing a song so the man knows where they are, so they don't get, cut in two. So this is great. But Abbott got in trouble back in the day with the PC crowd for treating women rather badly, and he had to point out that what the whole structure of this thing was actually a satire on some of the bizarre singularities in Victorian England. So it's kind of an interesting social phenomenon. He wasn't a mathematician, but he did do research, and his main interest apparently was the personality of Jesus Christ. So that was what he studied. All right, now I actually am pleased to say I have a very direct connection with this. I like to have direct connections with the things I talk about, and here's my direct connection, courtesy of Gary T. So this is a picture of Abbott and his friend Aldous, who was a student with him when they graduated. So what's my connection? Well, it's through Aldous. You see, Aldous, it turns out, was the second chairman of the mathematics department at Auckland University, which is where I was an undergraduate. So why the second? Well, he was the second because the first one was drowned in rather suspicious circumstances in Auckland Harbour, and everything was run. New Zealand was a colony and so on. So they sent for someone in England to come out and be the new chairman, and Aldous was the guy they picked. Whoops. No. So it was not a very good relationship with Aldous and the New Zealand mathematics department in Auckland, or rather Auckland University, because in fact they fired poor Aldous after a while because he had the audacity to hitch up his horse in the parking space reserved for the Chancellor's son. So, you know, even in university circles back then, parking was a big issue. And, you know, so were the relationships between the higher administration and the faculty. So this is a problem that has, of course, continued. Anyway, I won't say any more about this book. I'll go on. So we're talking about the plane, but the plane, even in two dimensions, the plane is not the only player in the game. There are these other surfaces around, and I want to just say a few words about them so you know that you can be two-dimensional without being in the plane. So, for instance, the most glaring example, of course, is this what we mathematicians with a savant term as a surface of genus 0, which of course is a sphere, and we all know that we live on a sphere. So, right, the Earth is a sphere, and you can see these pictures from space, which are pretty convincing. Even though apparently there are still people around who believe, you know, in the flat Earth society, that we actually don't live on a sphere at all. We actually live in the plane. Well, good luck to them, you know. That's great. And in fact, in a sense, they're almost right because it's almost the plane. If you take your sphere and you sort of lie it, put it on the plane like that, and then you project. This is called stereographical projection. You take the North Pole and then you draw a straight line from North Pole through a point on the sphere, and you see where it hits that equatorial plane there. Then that gives you a correspondence between all of the points on the plane and all of the points on the sphere, except, of course, the North Pole. So the moral is that if you take the North Pole away, then stereographical projection makes the sphere into the plane. So in most of the questions that I'm going to be talking about, you can replace the plane by the sphere and not really change anything. So that, anyway, as I said, there's more surfaces around than this one of genus 0. Here's another one. This is a surface of genus 1, and it's called genus 1 because there's this hole in it. You can't quite see through this. So this is a slightly inadequate picture, but this hole goes right through. As you know, this is a donut. It's not the same. You can't just take a point off away from the donut and then project it all down and get the plane. If you want to make it look like the plane, you have to do a much more radical cut on the surface. So that's a surface of genus 1, and here's another surface of genus 1. This is a tired old mathematician's joke, but it's somehow irresistible. This is a, whoops, sorry, this is Berkeley, I can't quite get away. This is a mug, and you know, for a topologist, for a mathematician, supposed to be the definition of a topologist is someone who can't tell the difference between a donut and a mug, because this also has its hole here, and if the rest of the surface will scrunch down, and you could, by continuous deformation, even a smooth deformation, make this into a donut. Okay, so that's the surface of genus 1. It's genus 1 because there's one hole. So what's next? Genus 1. Genus 3, right? I skipped this because I couldn't find any pretzels that only had 2 holes, but I had this little bag from the airplane with these horrible pretzels that they give you, and my wife said to me, "Why did you open that? You hate those things." And I said, "Yes, but I had to take a picture for my trip." So that's a surface of genus 3, and the genus 3 means there's 3 holes. So the surface of this pretzel is a surface of genus 3. So there are these two-dimensional spaces, which are not the plane, but they're locally like the plane. If you were a tiny little, well, even smaller than an ant, and you were sitting on this pretzel, then like the people in the Flat Earth Society, you would say, well, this is the plane, right? You wouldn't know the difference. All right. Next up, I know I've forgotten for the first time what's the next slide. Let me have a quick look. Cheat, it's blank. Great. Okay. Right. So on lies, white lies, downright lies, exaggeration, and a tangled web of fraud and deception. So yeah, I'm not actually talking about the White House. I'm talking about the typical mathematics or science public lecture. You see, whenever talk about one of these things, it's always complicated, right? There's a whole lot of details around it, and if you were to spend your time making sure that you got everything right, then A, everyone would be totally bored, and B, you would never get to the end of your talk. So in the interests of the story, if you like, I'm going to tell lies all the time, make things that are approximately true, but and near enough to keep the narrative going. So, with this in mind, if anyone really objects if I go too far, then we'll talk about it afterwards. Maybe we'll go outside. So. All right. So this is a very convenient excuse, by the way, if you're giving a talk. It means you don't really have to check up on your facts or anything like that. You can just, refer back to this slide all the time. All right. I've already given you a few of these lies, but there'll be plenty more to come, and a lot more tomorrow in tomorrow's lecture. So, we're talking about the plane. So I want to basically go over several things that are quite special on the plane, a lot of which can be understood by a non-mathematical person. The first, of course, is the famous four-color theorem. So this is the theorem that says any map in the plane can be colored using only four colors, maybe even less than four colors, but four colors will actually suffice. So this is a map, of course, you will all recognize California, at least as it is at the moment. Maybe there will be slightly more complicated after the elections. But so these are the counties in California, and you'll actually notice that there has been four colors used here. There's this green, yellow, this red, and this murky sort of brown color, and that works. So coloring means that, of course, if two countries are next door to each other, they have different colors. But in fact, it's not okay, because the rest of the world, for instance, the Pacific Ocean or Nevada or they should also have colors. And if you look at this, the sea would have to be a different color, but let's say it's white as it is. Well, that's a fifth color, and you can't replace it by green because it would be next to Santa Barbara here, or red, or yellow, or brown. So, oh my God, this is, well, I mean, the point is that you could recolor the whole thing. The four-color theorem says that you could recolor the whole thing with only four colors, and the sea and Arizona or whatever would all be colored with different colors. Okay, so this is the famous four-color theorem, and it's completely useless because we got plenty of colors, We're not really limited to four colors. And most of the maps that you see, it took me quite a while to find a map where they did only use four colors, because mostly if you want to make things clear, you will use 6 or 7 colors, and you also want to have things, if several things meet at the fork, you want all of those things around the fork to have different colors, for instance. However, as a mathematical thing, it is true that you can color any map on the plane using four colors. So this particular theorem has an interesting history. There was the odd false proof way back when, and it was put forward in the 19th century, and it was finally solved by Apple and Harkin and their computer in 1976. So they had a beautiful theory, which is based, of course, on a lot of good work of people coming before, and they reduced this thing to a lot of cases, and they had to check various things about all of these cases, and it wasn't doable by hand, so they got a computer to do it, and it went through all these cases. And as far as I know, I may be wrong, but there's been progress recently, but I think even now computers have to actually play a role in the solution. No one has the time. They might have the energy, but not the time to actually go through and check all of these different cases. So, as I say here, it was the first major problem solved by computer, and it led to the serious debate on the legitimacy of computer proofs in mathematics. Nowadays, we tend to think a little bit less. We seem to be a little less shocked, shall we say, about using a computer to prove a mathematical theorem. And we're more concerned really that, that the computer proof hasn't given us any more understanding of what's going on than that maybe the computer might be wrong, okay? We haven't really proved that the computer is wrong. I mean, there's programs that check automatically that a computer programmer didn't make a mistake, but maybe they're wrong and so on. So it's a serious issue in philosophical terms, but we also all know that from our own experience in all kinds of problems that the computer is far more likely to be right than we are in these things. So it's an interesting debate. It's an ongoing debate. And as I said, what we really worry about now is that a computer proof will actually not really enlighten us on what's actually happening. And that's true of the four-color theorem. If someone came up with a proof that had a real understanding, then that would still be a huge breakthrough, even though we know the theorem is true. Okay. So now, the plane, we're talking about the plane. Well, it turns out that the coloring problem of maps on higher genus surfaces is much easier. So for instance, you could look at maps that are not just on the plane or the sphere, but on the torus. They could have all countries. And then they could have more complicated connection pattern, because something could connect under here, back on the other side. So you would have, and it turns out, of course, that four colors do not suffice for maps drawn on the surface, but it's true that there's a seven-color theorem that on the torus, on the surface of genus 1, 7 colors suffice to color any map on the torus. And unlike the four-color theorem, this is old. This goes right back to the 19th century, and there is a proof that that 7 colors suffice and that you need 7 colors. And this proof can be explained, in the first part of a lecture. So the plane, this is the message. The plane somehow is the most difficult place to work in, or plane or genus 0. And that's what I'm going to try to emphasize with several other examples and things. But let's go on. I now want to talk about something slightly different, which is knots. And of course, one of the reasons I want to I'll say a little bit about my own work. And the other reason is that the knots give a compelling example of the adequacy of the plane. So I talked about how the plane was adequate to represent three-dimensional situations with perspective and how it's somehow embedded in our psyche. Well, here's an example, the theory of knots, where you can represent manifestly three-dimensional structures called knots by two-dimensional pictures. So by knots, I mean the knots that you tie in your shoelaces, regular knots, pieces of string in three-dimensional space, but they're certainly three-dimensional. And here's the proof that you can represent all knots. Here's a picture of a knot. It's just this piece of string. In mathematics, we often tie the ends together to make it a closed loop. We just draw this picture of the string going around and under itself and over itself. And with that information, we have completely represented the three-dimensional object, which is this knot, by a manifestly two-dimensional picture, right? You could take a piece of string and thread it through itself over and under and join the ends together, and you would have a three-dimensional object, completely defined by this two-dimensional, this planar picture. All right, so imagine we've done that, and then we take this piece of string and toss it in the air. Didn't hit this. And then come down and look how it landed, okay? Then we'll get another picture, and it won't be the same picture, will it? So the idea is that this three-dimensional knot can be represented in lots of different ways as pictures in the plane. So in that sense, the plane doesn't seem quite adequate, but it's fixable. There's this thing, two pictures give the same knot exactly when they differ by these Reidemeister moves, which are going to be planar objects. So I'll just quickly tell you about them. If you take a picture of a knot and you replace one of these strings, if you just put a kink in one of these strings, then as a three-dimensional object, you haven't changed it, have you? It's just the same, right? Just shuffle it around. Or if you take two of these, if you take two parallel pieces of string and push one over the other, then you haven't changed the three-dimensional thing that you represented. If you tied if you made the knot out of the picture after doing this, you would get the same knot as before doing this. And the last one is this most interesting one, this type 3 Reidemeister move, where I've sort of taken this thread there at the back and I've pushed it through to the other side. But once again, you can see, looking at it, that that's a three-dimensional thing that's happening, and it doesn't change the knot. You get the same knot if you apply any of these Reidemeister moves from the pictures. And there's a theorem, due to Reidemeister, which says that that's it, that two pictures give the same knot exactly when you can get from one picture to the other by the sequence of Reidemeister moves. So I went back to my knot that I made out of this string, and I threw it up in the air, and I got a new picture. Well, Reidemeister says I can take that new picture, I can apply a bunch of these moves and get back to the old picture. So I've recovered that very three-dimensional change by a two-dimensional picture. All right, well, mathematicians are not the only ones interested in knots by any means. There's been lots of decorative knots. This is a knot attributed to Leonardo for some reason. Maybe he even made it, I don't know. But what I want to point out is in the middle of this knot, there's a logo. It doesn't come out very well, but this is the logo of the International Guild of Knot Tiers. And it's also been my great fortune that because of my work in knot theory, I was elected honorary vice president for life of the Guild, of the International Guild of Knot Tiers, and that's been a source of great pride to me. And the Guild has its own journal, which is called Knotting Matters. And in case you don't believe me, there's the journal, and so I mean, you see that logo there. And to show my appreciation for being elected honorary vice president of the Guild, I tried to figure out something that I could do, to acknowledge this honor. So what I decided on was to write an article explaining, the mathematician's perspective on knots, and submitting it to the Guild, to Knotting Matters for publication. So I did this, and it took them a while to have a lot of reflection as to whether they should actually publish it. Don't forget, these are people who actually tie knots for a living, decorative knots, various versions of fishing knots and so on. But they did publish it in the end, and it can't say that it received immediate success or acclaim from the members of the Guild. In fact, there was the subsequent issue of the Guild, there was a sort of reply, an answer to my article from an old salt out on Long Island, who said, who does this professor think he is? He doesn't even know the difference between a knot and a grommet. Because apparently, when you tie the ends together, it's not a knot anymore. In the proper parlance, it's a grommet. So, in fact, the whole branch of mathematics should change its name. They should not be doing knot theory at all. They're doing grommet theory. So that hasn't had any success either. Anyway, it's been great. It's been great being a member of the Guild. Right, so I want to move one step on from knots. Another very closely related thing to knots is the theory of braids. So here's braid. This is actually my oldest daughter getting back in the story, but this time you really can't see her at all. But so this is a braid, a real braid that you do in your hair, and so mathematicians also have taken the terminology and the idea of braids and made it into the science. And so I want to explain what braids are briefly, because they will actually play a role later on. So braids are some kind of knots with boundary. So here's the idea. We take two bars, one at the top and one at the bottom, and those are going to be the boundary of the knot that we're going to draw. And we simply join these two bars, the one at the top and the one at the bottom, we join them with pieces of string, which go over and under each other just as they would if it were a knot. So that's a braid, and the special thing about braids, really special thing, is that once the string starts going down, it has to keep going down. It can never turn back up. So for instance, that that thing ruins, the fact that this goes up and around like that, this string comes down back, that's not a braid anymore. Okay, so braids are things, they're objects that are like that. And the relationship between braids and knots is the following, that if you, so I took that braid that I just drew, and then I took the tops of the strings, and I went round the back without introducing any more crossing, and joined all the tops to all of the bottoms. And then I take away the bar, and what do I have? I have a knot, okay? It's a rather special kind of knot, or rather special kind of picture of a knot, because it's always going round, because of that property of being braid, it's always going round and round and round and round and round. So in particular, at the very least, it has some special orientation on it. So there's a braid, and we went to a knot. Now there's an amazing theorem due to Alexander, and this is not the Macedonian, interested in knot theory. This is an American mathematician from the early 20th century, Alexander, who showed that, unlikely though it seems, any knot that you care to draw, like the one that we had on up before, any knot you can actually be rearranged in 3 dimensions, so it looks like this, that this is some kind of braid, and then you tie the bottoms to the tops of the braid. You get your knot. So, you know, I dare you to try it without any tutoring, but it is always possible. I was actually tutored myself by Joan Berman. She showed me how to do that, which was quite nice. And it turned out to be rather useful because you see there's a generalization yet of a braid, which is called a tangle, another version of a knot with boundary, which is a tangle, where you don't insist. Remember, for a braid, you insist that the strings, once they start coming down. Well, for a tangle, you don't insist on that at all. So you just get a mess, a tangle, right? Here's the boundary. Whoops. Tangle. Here's the boundary here, and here in the middle is just this tangle. Okay. So this, as you've already had a pre-glimpse, this is the kind of mess that you get into if you're involved in the sport of kiteboarding, which I am. So one of the things you have to do is, you know, even if you don't want to be, you're every now and again presented with a bunch of lines that have all got themselves into a big tangle, and then you've got to straighten them out. So why do you have to straighten them out? Well, this is rather important. Here's a schematic of what kite surfing is all about. You have a bar here which you hold on to, and then there's a kite which is about 20, 25 meters away from you. I love all these sports. You know, the units in windsurfing and kitesurfing, they're all total mixtures of square feet and square inches and square meters and meters rather than square meters. So, you know, this is a typical 7-meter kite that we have here, which is 7 square. Anyway, so there's this bar, and the bar is attached to the kite by some lines, typically 4, maybe 5 lines. And the point is that as a braid, if you think of these lines as being a braid, then this is a rather special braid. It's called the identity braid because all of the lines just go in parallel. And that's what you want to have at the end of the day when you connect your bar to your lines. Because if you don't, if you have a crossing here which shouldn't be there, then you could easily die, okay? And it's happened, believe me. You know, there's a decent wind out there. These can generate an enormous amount of pull and easily kill you. So you have to get this braid to be, you know, this tangle, you've got to end up being the identity braid, okay? So how do you do that? Well, you basically, so this is a picture of how you want it to end up. So going back, this is what you're faced with, or even worse, and this is what you have to end up with for survival reasons, right? It's not, you know, to prove some theorem or anything. You've got to do this because you want to be alive in half an hour. Okay, so what you do is you essentially do this Alexander thing. You start off with your tangle. Go back to the tangle. There it is. You see it's a mess there. And then you work on it until it becomes a braid. Okay, you see that once there, the lines are just going straight through from there to there. And once it's a braid, you can use your mathematics because the braids have the great advantage that they form a group. A group. You can compose braids putting one on top of the other, and there's an inverse. Given any braid, there's an inverse, and you want to reduce your braid to the identity braid, so you want to apply the inverse. Not only that, The braid has this nice presentation in terms of generators in relation, so I'm talking to the mathematicians here for a second. So you can apply, generator by generator, you can generate the inverse of your braid, and that is exactly what you do. You work through this braid until it comes out being the identity braid. So, and then you go and have some fun. But what I wanted to point out is that, every kite surfer, when he goes down to the beach and starts with this mess and is actually using two very mathematical things. First of all, this Alexander idea of turning a mess into a braid. And second, using the group structure of the braid to reduce an arbitrary braid to the identity braid. Okay? But I believe I'm the only kite surfer around who actually appreciates that when they actually do it. So, all right, so that's an interesting side about. All right, why did I do this? Because, as I said, I want to say something about my work, and the study of braids and their closures led to a knot polynomial. And here it is. So this is the simplest knot there is. This is the Trevorrow knot. And this is its polynomial. It's in the variable t, by the way. In the variable t. Not x. Normally polynomials are x, but this one, for some reason, gets to have t as its variable. Actually, one of the problems about the whole thing is no one has a damn clue about what this t means. So, all right, so the only thing to say here, really, of any interest is that if you looked at this knot in a mirror, then that would involve changing all the crossings, and this polynomial would become the same thing, but with 1 over t. So this would be t inverse plus t to the minus 3 minus t. So you would therefore conclude, since that's not the same polynomial, this knot and its mirror image are not the same. Well, that was a known fact, but it was kind of an easy way to do it. So that was one of the reasons why people got excited about this polynomial back in the day. All right, so now let me get on to algebra and planar algebra. So we're going to use the structure of the plane to do different kind of algebra. So what's ordinary algebra? So here's ordinary algebra. If you have a formula like 5 plus root 13 over 2 squared, some of you know why I chose that particular number, 5 plus root 13 over 2 squared, then how do you evaluate this? Well, you do a linear sequence of operations. First of all, you take the square root of 13, then you add it to 5, then you divide by 2, then you square the lot, and you get the answer. Okay, so that's algebra. And I would be tempted to use the word linear algebra for this, except unfortunately linear algebra is, that's like turning knot theory into grommet theory. So this is ordinary algebra, and what I'm proposing here is so-called planar algebra, which is, the idea is that instead of having a sequence of operations that do one after another, you do several, you combine several things at once. And the planar part of it is to do with what I'm going to call planar tangles. So this is a planar tangle. So this is it. So it's got planar tangle has one output disk, which is this big one here, and then it has a bunch of input disks. So the idea, let's get used to it from the start, we're going to put things in like the numbers 5, 13, and so on into that formula. We're going to put them into the input disks, and we're going to come out with something at the output. So this is the most general planar tangle. It's just an example. These blue things are strings, and they connect the input disks to the output disks, and they might connect the disks among themselves, or they might just be dangling freely. And the idea is to every such picture, this is just one such picture, there is an operation where you get to insert things into these input disks, and what you see is something in the output disk. So that's planar algebra. So operations modeled on this planar picture. All right, so what the idea is, you put in A, B, and C, and you get out, the answer is D. So this is just a formula in planar algebra, just like that. 5 plus root 13 over 2 squared was a formula in ordinary algebra. Okay, so planar algebra is a collection of objects which can be inserted into the internal disks of any planar tangle, such as A, B, and C in the picture, to get out another object, D. Right, I clicked again, I said it again. A planar algebra is a collection of objects. Okay, so here comes the first question about this. What might you want to put into those internal disks? Okay, and basically the rest of my talk is going to be some answers to that question. What might you want to put into them So you get something out at the end. Well, the first thing you might think of, late in the day, so we want to put in A, B, C, D, is you might want to put in some, some tasty dishes to get out a nice meal. But that's not what I'm here for, is it? I'm here to talk about mathematics, so let's do another one. So here's an answer that was proposed by John Conway, famous for, of course, for having invented, among other things, the game of life. What Conway suggested that we put in fact, he was the one responsible for the word tangle in this context. He suggested that we put in something we've already seen. We put in bits of knot. So here's the planar tangle. That's the planar tangle we saw before. Now I'm going to take as inputs bits of knot. So there, I've taken a bit of knot and I've stuck it in there. There, I've taken another bit of knot and I've stuck it in there. And there, I've taken another bit of knot and I've stuck it in there. Now I take away all of the input disks, just like I did with the braid, taking away the bars when I got knot. And look, I've got another bit of knot. Okay? So the answer is, the lesson is knots, bits of knot, form a planar algebra. They're things you can stick into a planar tangle and you get out another bit of knot. Right? So that's the first example, Conway. What else might one like to put in the internal disks? Well, here's another answer due to Roger Penrose, who was also famous for things called Penrose tilings, which I sad to say I didn't get a picture of. But anyway. So what Penrose suggested that you could put into these things is tensors. So this is slightly more mathematical than the previous one. You put in tensors. So if you start with your planar tangle, this one here, for instance, then I'm going to put a tensor in here, here, and here, and I'm going to get out a tensor. So I do that. So I put in a tensor A, and a tensor B, and a tensor C. Now what's a tensor? A tensor is just something that you give it indices and it gives you a number. So if we put in indices, a whole lot of indices here, one's around the boundary, and then we put indices on the internal strings as well, then the operation suggested by Penrose is just to what's called contraction. You contract over the indices that are connected by these strings. So in mathematical terms, the answer would be that D, with its indices I, J, K, and L, is the sum over P, Q, and R of these tensors. So this is actually a fancy Einstein summation convention. Einstein said that you sum over repeated indices. In this Penrose picture, you don't put in any indices at all. Remember, that is the Penrose way to do this contracted tensor. Okay. So now comes the crucial thing for this planar idea. I've been talking about planar tangles, but what's to stop you taking a different contraction system? So here I've drawn a tangle where the strings are allowed to cross. I guess I never said it, but I should have said it. What makes a tangle a planar tangle is that the strings don't cross. So here's one with the strings crossing, and you could just do a sum, just like we did for the planar tangle, with contracting over the internal indices, and you get an operation. So you immediately ask the question, why only planar connection systems? What's special about that? Well, I can give you one or two answers to that. I think I'm only going to give you one because time is pressing already. And the answer I'm going to give is, so excuse me, the non-mathematicians, give me a couple of minutes. You can go and think about, we're giving you a lot to think about. Give me a couple of minutes and I'll return to you in a second. So this is the theory of random matrices. If you want to do this integral, the limit, this integral trace of a to the n with this measure where dA is the Lebesgue measure on Hermitian matrices, and this V is maybe some polynomial in a potential, and lambda is a coupling constant, then there's a way to do this for finite capital N. You can do this and you expand, you take e to the lambda trace, sorry, there's a typo here, this trace should be up in the exponential. You don't do anything more complicated than expanding that exponential and then doing Gaussian integrals, and you get a huge sum. In this case, little n would be 8. Let's go back to it. Little n there, trace of 8 there. And then you have a bunch of pictures of this potential. This would be the coefficient. This would be contributing to the lambda to the fourth thing here, and you get a diagram like this, which is to be interpreted in the Penrose sense. Okay, so this is a whole lot of, you could generate a whole lot of Penrose tensor diagrams. But what's amazing is, if you take the limit as n tends to infinity, normalize everything so it converges, then all of the non-planar connection systems disappear. Okay, so this one that we had, this picture here, which corresponds to an integral, when you let capital N tend to infinity, this will simply disappear. It will tend to 0. Whereas this one will still be there because there's no crossings among the blue lines. Okay, so there's a reason, a very good mathematical reason, goes back to Tufte and perhaps before physicists, for looking at planar algebras rather than arbitrary algebras. Okay, so once again, here's a planar tangle. Planar algebra is a collection of objects which can be inserted into the internal disks to get another object. What else might you want to put in the pictures in the internal disks? Well, here's another answer. Also, I'm afraid aimed at mathematicians, but I will come back to it. So, relations in groups. So if you draw a picture like this is the tangle, the same formalism, and then you're in a group, and the group has elements with A, B, C, D, F, G, and you stick them on the strings of the tangle, and each time you read around the boundary here, A, C inverse, you take an inverse according to the orientation, A, C inverse, if every time on these internal disks here you get a relation in the group, then what you read around the boundary, which in this case would be A, B inverse G, is also a relation. Okay, I checked this, by the way, it's true. Whereas if you had a non-planar connection system, that wouldn't be true. Okay, so once again, the planar nature of these tangles is very important. And this, of course, some of you will recognize as the theory of Van-Kampen diagrams, which has had considerable success, in fact, in group theory. It's been used to do some non-trivial things. But now let me return to the general audience and ask the question. Planar algebra is a collection of objects, blah, blah, blah. This is about the 7th time, so I hope you've got it by now. So what else might you want to put in the internal disks? Now I'm going to go off in a different direction, which is basically the direction that physics also finds the plane very special. Not only does mathematics find the plane special, but physics does too. So here is a planar tangle, right? All I said about a planar tangle is it had to have input disks, output disks connected by strings. Well, there's a lot of input disks and one output disk, and they're connected by the strings. But that makes you think something completely different. It makes you think lattice. Maybe you could put spins in there. Maybe you could put molecules in there, so on. So that's what we want to do. And this was proposed, this kind of physics and the planar algebra stuff has been proposed as a method to make a quantum computer work by Michael Friedman. So Mike is a famous mathematician who solved the Poincare conjecture, topological Poincare conjecture in dimension 4. And then he switched. I have the greatest admiration for him because he's actually switched to a certain extent and started working on this approach to give the quantum computer. And of course, he won the Fields Medal for his contribution, for his Poincare conjecture. Now, the quantum computer was actually initially proposed by this gentleman, Feynman, who had the idea of using quantum mechanics to get a super good computer. And Feynman, he didn't get the Fields Medal. He got that other prize. You know, what's it called? Anyway, so this is, now I just want to say what the public conception is, perhaps, of the quantum computer. So some people think that you can just go into Walmart and buy yourself a quantum computer off the shelf. Some people think that the US, you know, there's some area 57 or something where there's a quantum computer in great secrecy in the middle of the desert somewhere. Some people imagine that a quantum computer consists of a bunch of lasers. Here's the standard mathematician's view of your quantum computer. But you know, the best picture by far that I've ever seen of a quantum computer is the one I'm about to show you, which is this one. Because you know, if you know quantum mechanics, you know there's this Schrodinger's cat. Well, you know, it's half dead and half alive. Well, there it is. It's a quantum computer. All right, now no, I've still got a little bit of time, so let me try to say something serious here at the end about how braids get into this. So the idea, as I said, is that in 2 dimensions, physics is a bit different from in 3 dimensions, and that is because when you exchange things in 2 dimensions, there's necessarily a sense. You go around clockwise or counterclockwise, whereas in 3 dimensions you don't have to. So this is the idea that, so let's take 3 points and start moving them around here. So I'm going to have these 3 points, and I'm going to move the top one around that way, this one around this way. I'm going to leave the middle one fixed, and I'm going to do a motion of 3 points in 2 dimensions. So there it is. Well, what I claim is what we're actually looking at is a braid. Okay? So not for nothing did I talk about all these braids. It wasn't just for kiteboarding. So I want to look at that picture in a slightly different way, and I want to actually follow it with time as a variable. So here's the points, and I'm going to make them do that dance that they just did, the 2 outside ones going around the middle one, but I'm going to follow that with time as they go up there. And what do you see? There's the middle one just going straight up, nothing's happening to it. And there's this one here starting to go around, and there's the other one starting to go around the other way, and they keep on going, and they form a braid. Well, if you've been watching, you'll see that's okay. You can get rid of that kink. It really is a braid if you looked at it from a slightly different angle. That was actually supposed to be a joke, but very seldom have I had an audience enjoy that joke. Should probably get rid of it. So there's a picture of that as a braid, and a more familiar kind of picture of the braid. And you also, if you know anything about quantum mechanics, you'll know that whenever you had to do something in quantum mechanics, it's supposed to be a matrix that goes with it, right? It was also called matrix mechanics, as much as quantum mechanics. Maybe it should be. So this particular braid has that matrix associated to it in one of these theories to make the quantum computer go. And these are the simplest braids, and they have these 2 matrices that get them. And there's this number t, and that number t is the same t as the t in that polynomial for Trevorrow. Okay. So, you may wonder why this one's so complicated compared to this one. Well, if anyone wants to know, I can explain it afterwards. All right, so the physical phenomenon that has been proposed most for doing this so where physics decides it's special in 2 dimensions, is the quantum Hall effect. Now, the quantum Hall effect, there's a classical Hall effect, which I've tried to illustrate here. You have a bit of stuff, it's called, you can't read that, it's called a prism in this picture here, bit of stuff, and then you have a magnetic field going vertically, and then you run a current through that way, and a voltage is produced across this bit of stuff, this prism, and you read that off, and that's the Hall effect, and it was a great thing because apparently Maxwell said it wouldn't happen. So Maxwell said this is not going to be what's happened, but it does happen. And then, of course, you have a quantum version of it where you, instead of having a nice straight line as for the voltage, as you apply as you change the external field, voltage should go up like that, but it doesn't in quantum world. It goes up and fits and starts and has plateaus and things like that. So that's the fractional quantum Hall effect. And as I said, as with the quantum computer itself, there's lots of visions of what this quantum Hall effect is about. This is the vision in which you see some kind of electron cloud in the quantum Hall effect. And this is the vision where you actually do the experiment. You're in the lab and you're fiddling with things and turning knobs and kind of thing. And so, yeah, it's interesting in that it is said of these labs, now get this one, it is said of these labs that they are the coldest places in the universe. Okay, not often you get to say with any confidence that something is the coldest place in the universe, but think about it. The temperatures that are reached, actually Bose-Einstein condensates get colder, but the temperatures that are reached in these labs are much, much colder than, the background radiation, or if you go into the middle of space way away from any stars or something, it's cold, but it's not that cold. So unless there's some other intelligent species out there which is also doing experiments on the quantum Hall effect, then we win. This is actually the coldest place in the universe. Get that. All right. So, so you know, so there's been lots of Nobel Prizes associated with this, with all this stuff, and I'm sure if anyone gets the quantum computer to work using this or any other method, there'll be more Nobel Prizes. But I'd like to end the talk just on a very wholesome note, reflecting on, you know, the fact that you have to get really, really low temperatures to get these good things to happen. So I'd just like to end with this idea that what people are actually trying to do is build a really good fridge. Okay, thanks for listening.